Organic compounds are generally made of the same 4 or 5 elements built in very complex structures, and so naming them is a challenging thing to do for the simple fact that you can't just simply roll call the elements. You don't learn much from that. So the last thing we're going to do this week is a basic crash course in organic nomenclature, or naming organic compounds. There are 3 rules of thumb I want you to keep in mind as we go through the nitty-gritty. Number 1, the molecule is generally not named after the number of carbons in it. It is specifically named after the length of the longest continuous chain that you have. That allows us to treat big, complex, branched, ringed structures as essentially one long chain or one ring with other stuff attached to it. Rule number 2, the more important something is, the closer to the end of the name it ends up. So in general, the last few syllables are going to include the length of that longest chain. You might hear something like pentane, or heptane, or decane, or propane, which I know doesn't sound like one of the prefixes you're used to. There are a couple new ones we're going to learn in a moment. Any substituents, anything that is branching off, any halogen atoms for that matter as well, chlorine, bromine, iodine, those are going to be up front at the beginning of the name, almost like an adjective. Now, as for functional groups, those are super important. So functional groups are going to change the suffix. Essentially, if I have something that is a pentane, 5 carbons long, if it's got a double bond in it, I'll call it pentene, because it's an alkene. We'll learn how to deal with a couple of those as we go along too. Third and final rule of thumb. Just like Roman numerals, when you see numbers in these names, they don't mean how many you have of anything. In this case, what the numbers are saying is, where on that chain should I put this substituent? So if I have a chlorine atom on the first carbon of a 5-carbon chain, I will call it 1-chloropentane. I'm going to name it that way to tell you where it is, but if it's on the second carbon, it'll be 2-chloro. Third carbon, 3-chloro. Those are your rules of thumb. Let's get into the particulars and try some of these out for ourselves. Okay, so first off, I told you there are a few new names we're going to have to learn here. So the first 4 names for alkanes, or just simple straight chain alkanes, don't follow the Greek prefixes we're accustomed to. Once you get to 5, they'll look very familiar. I mentioned a few times at the beginning here, pentane is what I call a 5-carbon long alkane. C6H14 would be hexane, and so on and so forth. 7 is heptane, 8 is octane, 9 is nonane, 10 is decane. These first 4 are weirdos though, and so we'll just have to kind of get used to them. CH4 is referred to as methane. This is what will come out of your Bunsen burners when you use them in week 9. C2H6 is ethane. You may have even heard this eth part beforehand. Ethyl alcohol, or ethanol, is the 2-carbon alcohol that's present in beer and wine and spirits and things like that. C3H8, you probably know if you're an avid griller. Propane is the name for a 3-carbon alkane. And for a 4-carbon alkane, this is butane, which you'll find in most cigarette lighters because butane has a boiling point very close to room temperature. And so if you keep it under pressure, it's able to stay in the liquid phase. Now, in biochemistry, we frequently encounter carbon rings, and those carbon rings we said are referred to as cycloalkanes. Well, that's also how we're going to adjust the name. Instead of just calling this thing pentane and that thing pentane, I call this cyclopentane, and that's how I tell you it's a ring. So as we established at the beginning, the first thing you want to do when you look at an organic molecule is look for the longest continuous chain, or the biggest ring, and name it accordingly. Once you've done that, anything else that's attached needs to be named as a substituent. And so that would be potentially a branch, or as I mentioned here, a halogen atom that's hanging off. Halogens are not considered to be functional groups. Now, for an alkyl group, that is a carbon, a hydrocarbon substituent, all we do is use these same root words here, meth, eth, prop, but, pent, hex, and so forth, and we change the ending. We make it -il. And so what I would call a CH3, a single carbon hanging off of a chain, I would call that a methyl group. If I have 2 carbons hanging off the chain, it's a ethyl group. Notice this is C2H5. So if I had two carbons hanging off the chain, but they're hanging in different places, that wouldn't be an ethyl group. That would be two methyl groups, which I would actually name the same way I do in covalent nomenclature. I'd say that it was a dimethyl situation. C3H7, if you happen to get something this big, would be propyl. C5H9 would be butyl. I do want to point out a special one, but it's relatively common. This is a 3-carbon substituent, but usually if you call something a propyl substituent, it's those 3 carbons all in a row. So for instance, if I had propyl cyclopentane, it would look like this. I would have all 3 carbons hanging off of that. When it's done this way, where they branch at a certain point, this is actually referred to as an isopropyl substituent. So if I did the same thing here and I made this like that, this would be isopropyl pentane. Now as for the halogen atoms, the only thing we do is take the INE in their name and convert it to an O. So this isn't a chlorine substituent when it's attached, it's chloro. This would be bromo. And this would be iodo. So as we established, this is the basic idea. I'm going to come up here, I'm going to look for my longest continuous chain, which here is definitely a pentane, here it's a cyclopentane, and then I'm going to name whatever the substituent is. So I've turned this into propyl cyclopentane. And I could write that as all one word if I wanted to. We don't generally put spaces in here. This would be isopropyl pentane. But I do want to call one thing out. Here, I might be a little uncertain of where this thing should go. If somebody told me they had isopropyl pentane, I might have to ask, well, does it belong here? Or does it belong on one of these carbons? I need to know where to put my substituents. And so we said beforehand that the way we answer the question where is by doing a little bit of numbering. So in this case here, let's take a brief moment to do what we already know how to do. Pause the video and decide what you would call this and this. All right, the longest chain of carbons, since that's an iodine atom there, is just simply all 4 of these in a row. So this would be a butane, and crucially it would be an iodobutane. Over here, 1, 2, 3, 4, 5. I could also get 5 carbons by going 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it really doesn't matter how I count. This is going to be a pentane. And because it has a 2-carbon substituent, let's just consider this to be my main chain. And then here's my substituent. That would be ethyl pentane. Now here's where the numbering comes in. In the event that the substituent is closer to one side of the chain than the other, I'm going to start at the side closest to it and number the carbons. So for the iodine, it's closer to the top, so I'll number from the top. 1, 2, 3, 4. That would make this 2-iodobutane. This one over here, it honestly doesn't matter which side we start from, so don't have paralysis by analysis. Just recognize, doesn't matter what you do, you're going to get the same number in the end. 1, 2, 3, 4, 5. So it's going to be 3 ethyl pentane. Tip from me to you, if you're ever feeling paralyzed by this, just go ahead and try it from both sides and take the smaller number. If I'd done that starting from the bottom here, I would have said 1, 2, 3 iodobutane, and 2 is smaller. So I would go ahead and stick with the 2. Now the only last thing to know dealing with molecules that have multiple substituents is that when you have that, you're going to give each one of them its own number. It'll come right before you say the substituent. You're just going to list them in alphabetical order, and if you've got something in here multiple times, for instance 2 chlorine atoms or 2 methyl groups, you're going to use the same Greek prefixes you did when we were naming covalent compounds to say something like dimethyl or trichloro. And in that case, you'll need more than one number. Sorry, that should say several numbers. I think it looks good in the reader. I don't know what happened here. Anyhow, I'll go through it with this one, and then I'll ask you to try that one out before I reveal the answer to you. So here's how you would go about this one. Notice that whether I start from here or here, I'm still going to be able to connect 5 carbons to each other. So I'll go like this, in one case. I could also have started from the bottom one. I could also have ended on the top one. Either way, the best I can do is connecting 5 carbons, so we'll name this in general a pentane. Now that means the other 3 carbons here are substituents. 2 of them are attached here in a line. This is what we would call an ethyl substituent. This one up top is all by its lonesome. We'll call that a methyl substituent. And now all that's left is to do the numbering. Notice that here I have the ethyl substituent dead center, so that's not going to decide anything, but methyl's closer to the right, so I'll start counting on the right. 1, 2, 3, 4, 5. So with all that in place here, I can see the methyl group is at 2, the ethyl group is at 3, and now I'm going to do this in alphabetical order. So ethyl first, 3, ethyl, 2, methyl, pentane. With that, take a moment and try this one out. Pause the video, and when you come back, I'll show you how it's done. But give it the good college try first. All right, this time around, our longest continuous chain appears to be 6 carbons. Because if I start here, I have a branch point here, but if I branch to that, I'm done, and that's just 5. I can get another 2 going this way, and it doesn't particularly matter whether I go left or right at the top, but I'll just go right for the time being. So that makes this a hexane with a bunch of substituents. Now, those substituents are a methyl group here, and a methyl group there. Both of those are 1 carbon. So this is a situation where you would say it's a dimethyl molecule. You've got 2 methyl groups. You've also got a bromo and a chloro. Lastly, if I want to look at where to begin counting, here you've got something at the 2nd carbon from this side. You've also got something at the 2nd carbon from that side. So that's a tie you can't break. But the other 2 are closer to the top right. So we'll start counting from the top right to figure out where these are. So that's going to mean that my first methyl group is on carbon 2. My second methyl group and my chloro are both on carbon 3. And my bromine, my bromo, is on carbon 6. So putting all of this together, again, going in alphabetical order, bromo is the first thing, so 5 bromo, followed by chloro, 3 chloro, and then the 2 methyl groups, and those are at carbons 2 and 3. So we'll write that as 2, 3 dimethyl hexane. And I've run out of room, but here we go. There's the end of that name. So they do get pretty darn large, but essentially what you've told somebody who reads this to do is start by drawing 6 carbons in a row. On the 2nd and 3rd carbon, in from either side, doesn't matter which, put a pair of CH3s, put a pair of 1 carbon branches. And then on that 3rd carbon, which already has a methyl group, put a chlorine, and on the 5th carbon, all the way on the other side, put a bromine in. That's basically you being able to read this whole thing and work out what you've got. And while we're getting a lot of practice with you coming up with names right now, the final page of your worksheets will be a little bit of practice for you to draw things from these names. Now you'll notice the one thing missing from our toolkit right now is we don't know what that or that means just yet. So let's move over to functional groups.